Today's agenda is just to do basic questions and a revision of capacitance and meant for students who would like to understand capacitor. It's basic level video. Question number one, define capacitor. Okay. So capacitor is defined as what? So the answer to this question is, okay. So capacitor is a two terminal device that stores energy in the form of electric field. Okay. So if you see a capacitor, you would find there is an electric field that exists. Okay. This is a one marker. If you just write that it's a two-terminal device that stores energy in the form of electric field, this should be sufficient. Let's move on to the question number 2. All right. So the definition of capacitance, it is the ability of an object to store charge. All right, question number 3. What is the SI unit of capacitance? The capacitance SI unit is farad. Okay. You should know this. You will find this in all the numericals that farad is being used. So important question, what is the basic construction of a capacitor? All right, so let's talk about construction of a basic capacitor. So I will tell you how the capacitor is constructed and what are the various parts of a capacitor. So if you look into this diagram, these are the two plates. Okay, let's label the plates of a capacitor. So these are the two plates. Okay, plate number 1, I will just call these as plates of the capacitor. Plates of capacitor. Okay, some people call it the conducting plates. What do they call it? Conducting plates. Some people also call them as the electrodes. Okay, the terminals like a battery, but just a name, electrodes of a capacitor. Okay, so these are the two. So plate number 1 and plate number 2, these are conducting plates. Remember, they allow the electricity to pass through them. Then you can see there is a space between the two capacitors. You can see this empty space. Okay, this is the empty space between the capacitor. Empty space. This empty space is filled by a material called as dielectric. What are we discussing? Construction of a capacitor. 3 parts, 2 plates, 1 dielectric material. What is the quality of a dielectric? It does not allow any electricity to pass through it and is an insulator. What are the examples of dielectric? Air is a dielectric. So between the 2 plates, you can have air. Then you can have mica. And then you can have paper. So these are the various types of dielectrics that you can have. Okay. Now let's see what happens when the battery is connected to the 2 plates of the dielectric. So you can see I am connecting a battery to the 2 plates of a capacitor. So this is the way I will draw. You can draw positive or negative on any side. It really does not matter. This should be a straight line. Don't worry about it. All right. So this is your, so the circuit is complete now. Now the charge starts moving from the battery O to the, so this is the charge which is moving. And now it reaches the plate. See, plate is a good conductor. But the problem is when the charge reaches the plate, now the charge wants to move towards what? The charge wants to move towards the other plate, right? From here to here. This is what the charge wants to do. The charge wants to travel from one conducting plate to the second conducting plate. So the charge is willing to go, but the problem is dielectric is an insulator. So dielectric will not allow this charge movement which you see. The charges are willing to go, right? Because battery is sending the charge. This is a conducting plate. The conducting plate gets the charge and then wants to send the charge to the other plate. The problem is the dielectric, which is insulator. So what happens? The charges get trapped on the charges get trapped on the plate 1, on the plates, on the plate. Okay? Because dielectric does not allow the movement of charge. Because dielectric does not allow the charge residing on the plates to move. Okay, I've used the word trapped, and therefore that charge therefore gets accumulated on the plates, and that results in an electric field which gets created between the two plates. We'll talk about all these things. Basic construction, just remember, two plates, one insulator between them. The plates allow the current to pass through it. The dielectric does not allow the current to pass through it. When the battery is connected, the charges start flowing and get trapped on the plates because the dielectric will not allow any charge to pass through them across the plates. Thank you. All right, so next question is, when does a capacitor start charging? We've already discussed this, but again I will repeat. So what you do is you pick up two plates. Between the two plates, these are of equal size, okay, identical. Don't worry about my diagrams, okay, I will just try and make them equal. The charging starts only when you have a battery connected to the capacitor. So it is important that a battery is connected for the charging of a capacitor. So I'll just complete the circuit so that you can see how it is all drawn. Okay, and the battery is connected. So this space is what? You already know this space. This is always an insulator. The insulator is also known as dielectric, and this is a conducting plate, and this is also a conducting plate. So what is the answer? The capacitor starts charging upon connecting the two plates separated by an insulator with the battery. All right, so very important question on when does a capacitor stop charging. So if I draw a capacitor for you, okay, like this, the capacitor stops charging when there are two situations, okay, and you must know both the situations as a beginner student who is new to the world of capacitor. So if you have a battery connected to the capacitor, okay, I'm drawing this circuit so that you can really learn how to connect the battery to the electrodes. The plates are also called as electrodes, terminals, like a battery terminal. They're electrodes because they also have charge accumulated on them. So if you look into this diagram, if the battery is of voltage V and you are able to finally the potential between the two plates, these two plates or the conducting plates, as the charge gets accumulated, the potential difference arises between these two plates, the conducting plates, and if it becomes equal to V, no more charging will happen because these two are of equal and opposite charges. So the capacitor stops charging, number one, when the potential difference between the two plates where the charge accumulates becomes equal to the battery's potential difference, or right, or the EMF. Generally we will use the word potential difference. So when these two become equal, the capacitor will stop further charging. The second situation is you remove the battery. After some charging, you remove the battery, right? And further charging will stop. Second situation is you remove the battery. As simple as that. Remove the battery, and the capacitor will stop charging. All right, so the question is, what happens if the battery is removed from the capacitor? So this is the, it's a good question to attempt. So what we do is we quickly draw a capacitor and we remove the battery from the capacitor. So the battery did charge the capacitor. So the actual question is, what happens to the charge once the battery is removed? We know it stops charging, but what happens to the accumulated charges here, right? So whatever charges are already stored here, what happens to those charges? So the answer is, if you remove the battery, the charge stays on the capacitor. So removal of battery will not mean that the charge will go away from the capacitor. Whatever charge it acquires when you connect the battery and then you remove the battery, that charge will permanently stay on the capacitor. This is the answer. You will not lose the charge. It will stay on the conducting plates. So the exact question is, what are the factors that determine the amount of capacitance in a capacitor? All right. So first is the area. Okay. The area of the conducting plates. Area of the conducting plates. Okay. This is one. The second is the spacing between the conducting plates or the electrodes. Third, the type of dielectric you put between the two conducting plates. So dielectric type also decides, or the medium, it is also called as dielectric medium. So air is an example, right? So if you put air, the capacitance will change. If you put mica, the capacitance will change. If you put paper between the two plates, the capacitance will change. So these are the three factors that decide the overall capacitance in a capacitor. All right, so this is a very important question. The capacitance of a parallel plate capacitor is written as epsilon naught epsilon r into A divided by D. How do what does it mean? So this epsilon naught is the permittivity of air or vacuum. Okay, and what is epsilon r? This is relative permittivity of air. All right, so very important question, and you must understand each of the terms if you're a beginner. Okay, what is the formula for the parallel plate capacitor? So the capacitor we are studying, I've been showing this diagram to you. This is a parallel plate capacitor. The plates are like this. Okay, this is a plate. Okay, conducting plate. It allows the current to pass through it. The area of this plate is A, and the separation between the two plates, okay, these two plates, which are actually like this, two plates, is D. So the separation between the two plates is D. So let me just write the complete formula. The capacitance is given by epsilon naught, epsilon R, okay, A divided by D. Now I will explain you each of the terms. Epsilon naught is the permittivity of air. Permittivity of air. Okay. Epsilon naught R is the relative permittivity. Relative permittivity of the dielectric medium, which is like mica, paper, which is introduced, right? They have values. A is the area of the plates. What is D? Separation between the plates. Okay. Now, it is very important that you understand, and the next question will deal with what is the meaning of these two things. Okay, area I think is very clear. It is expressed in centimeter square, meter square. D is in centimeter or meter or millimeter. It's basically the separation between the two plates. So you draw the two plates like these. They are parallel to each other, right? There is a parallel word. The distance between these two is capital D. The distance between the area of the plates is A, and the medium which is between these two plates. Now that medium can be air. If it is air, then we use epsilon naught. If it is another medium like mica or paper, we use additionally epsilon R. In the next question, we will discuss the meaning of the word permittivity and what is the significance of permittivity. All right, so this concept is a bit difficult to understand, but we will try to make it simple. So if you have a parallel plate capacitor, okay, a parallel plate capacitor like this, what you see in front of you as a diagram is generally you have vacuum or air in between these two. Okay, so the vacuum is between these two plates. So you can see these are the two plates and you have vacuum. Okay, vacuum or air, one and the same thing. All right, so either you can use vacuum or you can have air as the medium between the two. Now, sometimes what they do is they replace, and what they do is insert, a mica, for example. So sometimes a paper can be used, sometimes a mica can be used, even oil can be used, plastic can be used. They are the insulators, right? I hope you remember. See, air is also an insulator. Any form of insulator will help. So let's concentrate on understanding what the concept of permittivity. So if you see in the second diagram, I have introduced a material, and this material which I have introduced, okay, is another insulator. It's an insulator, or what is commonly called as a dielectric. Okay, dielectric, one and the same thing. So remember, see the words very carefully. See, vacuum also is an insulator. A vacuum also is an insulator. What is an insulator? What is an insulator? If I were to say insulator, right, which does not have any free electron. So even if you apply a battery to an insulator, no current will flow. So insulators have no extra electron for, like metals. Metals have extra electrons that helps in flow of electricity. Insulator has nothing. So examples of insulator, vacuum is an example, the simplest one. When we study vacuum, or air, it is generally one and the same thing. The the properties of vacuum and air are almost same, but when we introduce a dielectric, another material, remember the word material, no, like mica. Okay, so mica is a material. Okay, paper is a material. So these are materials which are also called as dielectrics. Dielectric medium, you will see the medium, right? So if you see the expression of capacitance, it is given by, right, this. I told you about epsilon naught. Okay, very basic for beginner level students, epsilon r, and then we wrote area of the plate divided by the distance between. This epsilon naught is for the vacuum or the air. Okay, the permittivity of vacuum or air, and this is the epsilon r, is the property of the material. We will talk about the property later, as compared to the vacuum. So it's called relative permittivity. I hope you saw that, right? It is called as relative permittivity, right? Just check the spellings. I think I didn't spell it properly in the last question. It is epsilon r. Okay. So the point I'm trying to make, that the material, if you can see the formula of capacitance, it is proportional to epsilon naught, epsilon r. Okay. So capacitance of a parallel plate capacitor is dependent on the type of dielectric you choose, type of dielectric used. It is very much dependent on type of dielectric. So if you choose mica, you can get a different capacitance. If you use paper, you will get a different capacitance, because the value of epsilon r is different for mica. So you will write epsilon mica. Okay, epsilon paper. The values are given in the questions when you solve them. Okay. What is permittivity? What is dielectric constant? I have not defined it, but I'm telling you it has something to do with the property of the material. So capacitance is dependent on three things: area of the parallel plate capacitors, the spacing between them, and then of course the type of material or the type of dielectric you will use. Okay, now let's discuss in brief some details of the use of this insulator. So they see this. Let's understand. What are the functions which are uh, done by this insulating layer, or the layer between the two parallel plates. Okay, so let me put some material between these two. Okay, if I put this material between these two, okay, this is some material I'm just representing with lines. You can put any type of line between these two. Okay, I'm using some angle, line at an angle to show a material, but some people can show it any way you want to. You can also show it like this. Okay, you can just show it like a a straight line also, but generally I tend to show it like an inclined plane. Anyway, see, first thing is these two plates which you see, the conducting plates, have a force of attraction. So this dielectric, okay, this dielectric, number one, acts as a separator. Okay, it acts as a separator. You know that these two conducting plates have charges on them, and there is a force of attraction. Force of attraction, right? So this dielectric that you introduce keeps them separate. So The dielectric acts as a separator. Second thing which happens is the dielectric reduces the electric field between the parallel plate capacitors. So if you have an electric field E here, which is in the vacuum, for example, you have vacuum here, it is okay. So this is electric field in vacuum. If you introduce a dielectric of relative permittivity of epsilon r, the new electric field will be given by epsilon naught divided by, electric field will be given by E naught, electric field in vacuum divided by epsilon r. So second job, if you can see epsilon r, remember, is always greater than 1 because the property which we are referring to, insulating property for the vacuum is less, and for insulators like mica and paper or oil, it is more than air. So relative permittivity, we will discuss what it is. It is a bit complicated. Let's do the basics first. Separator, second is it reduces the electric field between the two plates. Let's talk about the third. We are talking about the various functions of insulator. What is insulator being used for? It's used as a separator because there is a lot of force of attraction. It keeps the two attracting plates separate. Second, it reduces the electric field between the two plates. And the third use of an insulator or a dielectric, one and the same thing. Okay, don't get confused. Dielectric means insulator only. All right, so the third use is prevent dielectric breakdown. Okay, I will tell you what dielectric breakdown is. See, sometimes, when you have vacuum, for example, this is a case of vacuum, there is an electric field between the two plates. Okay, so there is definitely an electric field between the two plates, which I am showing you now. Okay, because there are two charges. So electric field is imminent, right? It has to be there. There is no choice. So you have electric field which is between the two plates like this. Okay. If the distance between these two plates is very small, okay, which is a spacing, D is very small, then what happens is the electric field which is given by V by D can become very high. Okay. And when it becomes very high, it becomes so high that it breaks the insulating property of the vacuum. So what you see is sparking here. Because electric field is so high, it breaks down the insulating properties of the insulator. But if you introduce a material like this, dielectric material, you cannot break it down using a very high electric field. So when I say it prevents electric breakdown, I mean the capability to tolerate, capability to tolerate high electric fields without getting damaged. High electric fields without losing its insulating property. So you will see a lot of sparks. You might have seen sparking happening in the wire. That is because the insulators which are there in the wire near your house, right, which are supplying electricity to you, there are insulators, round insulators, right? So the charge flows through them. Normally, charge cannot flow through them. That is why they're applied. But the moment you have very high electric field, the charge is able to flow, right? So insulators though don't allow the charge to flow through them, but when high electric field is there, they allow the charge to pass through them. They lose their property and they break down. That is known as dielectric breakdown, that it has failed to do its job. So the capability to tolerate high electric field without losing insulating properties. So this is not a very accurate definition, but for the purpose we are doing, it is enough. We can go into the microscopic details of dielectric. I have a lot of videos that explain what is a dielectric. So, but currently my focus is what? Capacitance. I'm not worried about the exact meaning of the word permittivity. Okay. So whenever you see the words like dielectric constant, dielectric constant, okay, dielectric constant, you see words like relative permittivity, don't be scared. Okay, don't be scared. It is nothing. It is the material which is inserted between the capacitor. It's some property of that material. What is it used for? We have already discussed. And how does it impact the capacitance? If the capacitance in air is C naught or vacuum is C naught of a parallel plate capacitor, the capacitance goes up when you introduce a material. So if you introduce a material, the capacitance will go up by a factor of epsilon naught R, which is a relative permittivity. Okay, so epsilon R into C vacuum. This is your new capacitance of a parallel plate capacitor when a dielectric of relative permittivity epsilon naught R is increased. So if you see the word, the dielectric constant of a medium is 2, right? And the capacitance is given to be 2 microfarad in air. Okay, then what is a new capacitance? You will just say it is relative permittivity or dielectric constant multiplied by whatever is in the air. So the new capacitance will become 4 microfarad. So remember, the material between the capacitance has an impact on the capacitance. It is very important to worry about the type of material that you introduce between the capacitor. It is able to change the capacitance value. It is dimensionless. It is a ratio. Okay, as you can see, it is defined as a ratio. You can write it as the capacitance when dielectric is there divided by the capacitance when dielectric is not there and only vacuum is there. Vacuum as a dielectric, this is the capacitance. In terms of electric field also, it can be written as electric field when dielectric is there divided by electric field when dielectric is not there. Dielectric as in mica, paper. Dielectric is always there because vacuum and air also are dielectric, but their permittivity is considered to be 1, relative permittivity, okay, compared to themselves. So it's a dimensionless quantity. Permittivity is 2. It has nothing, but capacitance is 2 microfarad. So I hope it is clear. Some basics of capacitance are clear. This last part of dielectric is a bit complicated, but your key takeaway is that if you see a question that has dielectric mentioned, you will know immediately now the capacitance will go up because we are introducing a material between the two plates. And depending on the material, you can put the value of epsilon R. This is called epsilon. Okay, epsilon. This is epsilon naught. That is the permittivity of vacuum or air. This value. Okay, vacuum air permittivity is written like this. We will discuss. I have many videos on the chapter of capacitance. You can go through them. Today I wanted to do something for the students who are beginner, who are early into this game and want to understand the basics of a capacitor or capacitance definitions, 1 markers, basic concepts of a capacitor. But even if you're an advanced level students, you will definitely gain something out of this.